like to acknowledge my co-author, several of my former and current students, as well as my colleague, Professor Sunil Kodambaka at UCLA. So for the past several years, we have been working on exploring the mechanisms controlling the room temp plasticity of several group 4 and group 5 transition metal carbide under the sponsorship of the Air Force Office of Scientific Research, as well as the National Science Foundation. So, here is the outline of my talk. So I'll briefly go through the background and experimental approach, and then I will discuss several in-situ nano-mechanical testing, including in-situ TEM nano-compression test of several carbide pillars. And then I'll talk about using density function theory to simulate or to explore the atomic scale mechanisms which control the plastic deformation. And then I'll talk about the in-situ SEM microcompression of different refractory carbides, and then a brief summary. So as we know that transition metal carbides, including zirconia carbide, hafnium carbide, tantalum carbide, and niobium carbides, they are attractive materials for ultra-high temperature applications. Okay. This is because they have many very attractive properties, including very high melting temperature. Most of them, as you can see in the figure, are over 3000 degrees C. They have very high hardness, very high Young's modulus, very good chemical stability, and high strength at elevated temperatures. So potential application of these materials include the hypersonic vehicles, as well as high temperature shieldings and engines. Okay. But as we know that transition metal carbides are generally considered to be very brittle at room temperature, and due to its very limited dislocation activities. But the previous investigation have demonstrated that this material can be ductile at elevated temperatures. As I mentioned, that these transition metal carbide are generally considered to be brittle at room temp. Okay. But the previous investigation using high temperature compression test of zirconia carbide single crystal revealed that several step systems are operative with nearly identical critical resolved shear stress. This provides some light suggesting that the possibility of realizing the ductility in polycrystalline zirconia carbide. However, over the several decades, the bulk plasticity in these ceramics was never realized. Okay? So the ductile ceramic is still one of the holy grails of material science and for ceramic communities. So as we know that a significant ductile ceramic require dislocation plasticity at room temperatures. So here essentially is a list of what is lacking for our quest of ductile ceramics at room temp. Okay. So we need to have a detailed atomic scale understanding of the process controlling the material behavior. And we also need to have an experimental technique which will allow us to in situ characterize the atomic scale, a description of the microstructure, morphological and compositional evolution in these materials and their relationship to its mechanical properties. Okay. And so, interestingly, in the past several years, the advances in sample preparation technique, as well as the in-situ nano and micro-mechanical testing capabilities have opened up these new opportunities for us to explore the origins of room temperature plasticity in these refractory metal carbides. So the material that we use initially were all single crystals. Okay, so the reason that we choose a single crystal is for many reasons. One is to eliminate the effect of grain boundary. Okay, and we can also set the foundation for a fundamental study on the effect of crystallographic orientation, structure, and size on the plasticity at room temperatures. So gradually we will expand our work from single to polycrystalline material and then to composites. And the test will be conducted from room temperature and at temperature over 1,000 degrees C. So these are some of the group 4 and group 5 transition metal carbides that we use, including zirconia carbide, tantalum carbide, niobium carbide, silicon carbide, and vanadium carbide. So in terms of the sample preparation, so we use an FEI Nova 600 dual beam FIB system to mill the pillars. Okay, so as you can see that these materials are very hard, so it's not very easy to prepare these fine diameter pillars. Okay, so as you can see that even after 40 minutes of FIB milling, okay, so you can just barely reveal some shape of the pillars. And here is more like a schematic flow of how we prepare a zirconia carbide nano pillar using the focused ion beam techniques. Okay. So as you can see that we start from a single crystal wafer, okay, and go through multiple stages of milling. Finally, we are able to obtain these pillars with different diameters ranging from about 100 nanometer up to several microns if we want to use it for in-situ SEM microcompression test. Okay. So after the sample preparation, okay, here is the setup for the in-situ TEM nanocompression test. Okay, so if we look at the right view, okay, so as you can see that this is an individual pillar, okay, and then we have a flat diamond punch, okay, so the diamond punch can be controlled at a certain loading rate, okay, to push or to compress the pillar. In the meantime, you have electron beam will come down perpendicular to the pillar. So essentially, we can position the indenter tip directly opposite the sample and perpendicular to the electron beam. Okay, so all the deformation event can be recorded as well as can be viewed in situ. So this, one of the limit for this in situ TEM holder essentially is that it has a relatively limited loading capability. So in this case, it's just a little over 1,000 micronewton of maximum force. As the size of the pillar become bigger, and then we need to use the in-situ SEM, the nanocompression test, to provide a much higher loading capacity. And this certainly this Hystertron pickle indenter has a very good resolution. As you can see that 0.1 micronewton of force noise flow, and as well as very good resolution in the displacement. So let me briefly show some of the results and also some of the unexpected discoveries that we've had. Okay, so this is a sequence of pictures that we took during the nano-compression test of zirconia carbide 100 single crystal. So as you can see that this is the T series of TEM image, okay? And here is the load versus displacement result that recorded. So we convert that into a stress versus a displacement curve. Okay, so as you can see that initially it's a linear elastic behavior, and but at the displacement of 60 nanometer, we can observe the first occurrence of shear, as you can see in this picture B. Okay, and then as we continue to load to compress the sample, essentially, okay, at the stage 2, as you can see that we can see clearly the formation of a surface step and the formation of a secondary second shear plane. Okay. So this is clearly an evidence of plastic deformation at room temperature. In the meantime, as we mentioned, that we can not only do an image, we can also do a selected area electron diffraction. So this SAED pattern clearly indicates that the pillar retains its single crystalline structure. There is no phase transformation, no twinning due to compression. And when we change a different crystallographic orientation, so this is the nano-compression test result for zirconia carbide 111. So for this one, clearly you see that it's not quite the same as in zirconia carbide 100. Okay. So from a series of these TEM image, and we see a nucleation, motion, and tangling of dislocation within the pillar. However, no slip traces were observed. Okay. So as you can see from the stress versus the displacement curve, okay, so we have a smooth and followed by nonlinear variation in displacement with applied load. Okay. And there is an absence of any abrupt change or pop-in associated with the slip. Okay. So again, this is quite consistent with a plastic deformation via dislocation motion. Okay. And again, if you look at the selected area electron diffraction pattern, so it also indicates that neither crystal structure nor crystallinity was affected during compression. Okay. So, so this is essentially the direct observation of the plastic deformation of zirconia carbide 100 and zirconia carbide 111 single crystal under uniaxial compression. So we are able to identify the slip systems which operate in these two crystallographic orientations. So we have also investigated the size scale effect. So as you can see that we have the zirconia carbide 111 and 100 single crystal, and the diameter of the pillars ranging from 100 nanometer up to about 500 nanometers. Okay, so again, through this stress and displacement curve, clearly, as I mentioned, that for zirconia carbide 100 and 111, and the deformation mechanisms are somewhat different. Okay. So from these stress displacement curve, okay, and we can extract the yield strengths as a function of the pillar diameters. Okay, so here is the sigma y, the yield strength, as a function of pillar diameter for these zirconia carbide single crystal with two crystallographic orientation. So, so essentially that all the pillars in each crystal orientation showed a similar behavior, okay, and in which the yield strength is increasing with decreasing diameter of the pillars. Okay, so this is a typical dislocation starvation and dislocation truncation in small-scale samples that lead to increased flow stress. Okay. So, but one very interesting observation is that the cornea carbide single crystal exhibit a strong size dependence, especially in the cornea carbide 111. As you can see that in 100, and the sigma y changed from about 6 to 9 GPa. However, at 111, it changed from about 0.5 to almost 10 GPa. Okay. So this is in contrast to what have been observed in lithium fluoride and magnesium oxide, in which the yield strengths in 100 exhibit a very strong size dependence compared to sigma y in 111 orientation. So to understand some of the anisotropies, and so we also use a density function theory calculation. So DFT calculation basically will provide us the atomic scale insight into the mechanical behavior of the transition metal carbides. Okay. So what we do essentially is to calculate the energy required to displace the atoms from their equilibrium positions and the ideal yield strength, shear stress, and energetics of dislocation nucleations can be estimated. So here is a typical result from the DFT calculation. So here is the uniaxial compression of the cornea carbide, 111, so in the red, and the blue is 100. So the compression of the cornea carbide along 111 is easier compared to the compression along 100. So the cornea carbide 111 is clearly softer than the cornea carbide 100. Okay. And we can also calculate unstable stacking for energies. Okay, essentially, this is the measurement of the resistance to dislocation nucleation. And we found that it's lowest along the slip system of 1, -0 plane and 111 orientation. So essentially, our conclusion is that through the DFT calculation is that the slip system of 001 plane 110 direction and 1 -1 plane and 110 direction are the soft and the hard slip system for the cornea carbide. So let me jump to the in-situ deformation behavior of tantalum carbide 100 pillar. And so again, this is a series of TEM pictures, and on the right is the stress versus the displacement curve. Okay, and again, as you can see that we have two pop-ins at different displacement level, which correspond to the picture here at 1 and also at 2 here. Okay. And so this is again the SAED, selected area electron diffraction pattern of the pillar. So essentially they indicate that there is no phase transformation. Okay. And also through the SAED, the diffraction pattern, we are able to identify the slip systems. And here is the tantalum carbide 011 pillars. Okay. And again, as you can see that on the left is a series of in-situ TEM image and selected area electron diffraction. And on the right is the stress versus the displacement curve. Okay. Again, as you can see that linear elastic behavior at 0.1, you can clearly see the shear plane. Okay. And we also investigate the size effect on tantalum carbide 100 and tantalum carbide 100 pillars. Okay, again, you can see that at different pillar diameters, Okay? So what we found here is that the yield strength from tantalum carbide 100 and tantalum carbide 111 is nearly independent of independent of the pillar diameter, even though okay, the yield strength slightly increase with decreasing diameter, but the change is not significant. But compared to these two crystallographic orientation, we found that tantalum carbide 100 pillar are overall softer compared to the tantalum carbide 1011 pillars. Okay. And again, this result is in contrary to what was I just mentioned for similar structure of zirconia carbide 100 and zirconia carbide 111. And again, we do DFT calculation and to identify stacking for energy. So as you can see from here, so clearly that based upon stacking for energy for various possible slip systems in tantalum carbide, so we have identified this 111 plane and 110 direction slip system, and as well as 110 plane and 110 direction as the two active slip systems. So if we compare the zirconia carbide and tantalum carbide, as we can see that for both crystals, the yield strengths vary with diameter and more change is observed for zirconia carbide 111. And zirconia carbide 111 is softer under uniaxial compression of zirconia compared to zirconia carbide 100. But tantalum carbide, on the other hand, does not follow the same trend. Okay? So we observe the differences on size and orientation dependence between the group 4 and group 5 transition metal carbides is because of the electronic structure of the transition metal carbide varies with the valence electron concentration in the lattice and the covalent radii of the metal cation, as well as crystal orientations. Okay. So in both zirconia carbide and tantalum carbide, we have identified the possible slip system. So let me summarize. So the in-situ nano and micro compression test and computational models that we have done shed light on the atomic scale deformation mechanism, room temperature dislocation, nucleation, and mobility, as well as a room-time plasticity in transition metal carbides. So we have clearly demonstrated that multiple slip systems can be active at room temperature, and plasticity could be expected in hard refractory transition metal carbide. So the result really have opened many doors of possibilities in designing new ductile ceramics, such as the design of polycrystalline transition metal carbide with tailored grain orientation and grain size distribution with potentially enhanced room-time ductility. We can design a hard but ductile nanocomposites, freestanding titanium transition metal carbide thin film, nanowire, and nanostructures for a variety of micro and nano-mechanical devices. Thank you.